We're going to look at another example of comparison test. So we're going to use the comparison test to determine if the series summation from 1 to infinity of sine squared of n divided by 4n to the 5th plus n, if this series converges or diverges. And also, we're going to determine if so we're going to determine if the series n equals 1 to infinity, 7 plus sine squared of 65 n to the 10th plus 3 divided by 3n, if this series converges or diverges. Okay, so once again we're going to really recall the two versions, the two parts of a comparison test that are valid, that will allow us to draw the conclusion. So suppose that the series starting at n sub naught to infinity of a sub n, and we have another series starting with n sub naught to infinity of b sub n. And both series have all positive terms. So a sub n positive, b sub n positive for every n. And here's the first part of it's called the convergence part of comparison test. If the b sub n series converges, and then the nth term of the a sub n series, namely a sub n, is always below or equal to b sub n, then the a sub n series must also converge. And then the divergence part of the comparison test is if the b sub n series diverges, and b sub n is always below a sub n, then the a sub n series diverges. So now we're going to review basic identity, the inequality for the sine square. Sine square really of anything is between 0 and 1. So one of our series has a sine squared of n, and here's the repeated or the more generalized version of this, sine squared of anything that is defined. So if we can plug in whatever value and it's defined, it's between 0 and 1 also. So we're going to use both of these appropriately to make the conclusions to determine the convergence or divergence of the two examples in this video. The first example is the summation from 1 to infinity of sine squared of n in the numerator divided by 4n to the fifth plus n in the. So we're going to take the denominator 4n to the fifth plus n, and this is greater than, of course, just n to the fifth. And then if we flip it, 1 over 4n to the fifth plus n will be less than 1 over n to the fifth power. Now let's multiply both numerators here by sine squared of n, and we have sine squared of n over 4n to the fifth plus n greater than 0, and in turn less than sine squared of n over n to the fifth. Now using the inequality that sine squared of n is less than or equal to 1, we can write that as less than or equal to 1 over n to the fifth. Let's call 1 over n to the fifth b sub n, and sine squared of n over 4n to the fifth plus n a sub n. We now examine convergence or divergence of the b sub n series. That's the summation 1 to infinity 1 over n to the fifth. This is a p series. It converges because p is equal to 5, which is greater than 1, and that's the determination of convergence. And so now let's make the conclusion. We have the a sub n series, which is equal to the summation from 1 to infinity sine squared of n divided by 4n to the fifth plus n is less than just the series from 1 to infinity 1 over n to the fifth, which we call the b sub n series. Since the b sub n series converges and the a sub n series is smaller than the b sub n series, we can now make the conclusion, the correct conclusion, that the series a sub n summation from 1 to infinity of sine squared of n over 4n to the fifth plus n, this series converges by comparison test. And let's look at the other example. The other example, the sine square term, is more complicated. So we have the summation from 1 to infinity. We have in the numerator 7 plus sine squared of 65 n to the 10th power plus 3. And in the denominator we have 3n. So here we're going to use the other inequality of sine square. So we know that sine square of anything is between 1 and 0. And here anything is 65n to the 10th plus 3. We're going to need the left part of the inequality, that the sine square term is greater or equal to 0. So 7 plus sine squared of 65 n to the 10th plus 3 divided by 3n is going to be greater than or equal to, the 7 will stay 7, but the sine square term is greater than or equal to 0. So we can write the numerator now 7 plus 0 and keep the denominator the same. So this is 7 over 3n. And we can call that our b sub n sequence, and then the 7 plus sine squared of 65n to the 10th plus 3 over 3n, our a sub n. You can see that a sub n is greater than or equal to b sub n. All we have to do is show that the b sub n series diverges, and we're going to do it by just showing that 1 over n diverges. We know there's really nothing to show. if we recognize this is the harmonic series, which we know diverges. So harmonic series, it diverges. If we multiply that by 7/3, that will not change the fact that the series diverges. It still diverges. So our B sub n series is just 7/3 times the harmonic series, summation from 1 to infinity, 7/3 times 1 over n. B sub n diverges. And that's really all we need. We now just want to state this one more time. We're considering the A sub n series, summation from 1 to infinity A sub n, which is in this case equals to summation from 1 to infinity of 7 plus sine squared of 65 n to the 10th plus 3 divided by 3n. We know that this series is greater than or equal to the summation from 1 to infinity 7 over 3n, which is the B sub n series. We know that the B sub n series diverges, and therefore the series we're considering, summation 1 to infinity A sub n, which in this case is 1 to infinity summation 7 plus sine squared of 65 n to the 10 plus 3 divided by 3n. And this series diverges. This is the second part of the comparison test, and we can say why it diverges by comparison test.